In this video, we are going to discuss how to calculate the area enclosed by two curves for x bounded between and lower limit a and b. To begin our discussion, let us consider two curves f and g. For x enclosed between a and b, we assume that the function f is always larger than the values of the function g. And with that, you would be able to define an area bounded between the curves of f and g and x between a and b. How would you calculate a of this area? The way how you do this is by performing an partitions between the two curves and a and b, then calculate the Riemann sum for this area. We have an upper curve f and lower curve we call g here. You make a partition of p where p is a partition obtained by forming n column between x equals to a and x equals to b. Each column has a width of delta I, where I index the column and I would then run from 1 to up to n, where n is the number of the column in the partition. In each column I, we choose a value ci that is sitting between x of I minus 1 and x of I. The values of the function sitting on the curve f at this particular values of x is then equal to x of ci, whereas the value for the function g at x equals to ci is then given by g of ci. So the height of the column hi, that is the difference between f at ci minus g at ci. Here I label it as hi. The area defined by the column is then delta ai, which is just the product of delta I, the width of the column, times the height of the column. Therefore, if you sum up all the delta ai, that is the area of each column in your partition, the first column, second column, third column, until the last column, the nth column, which you write it as I from 1 to I equals to n. This quantity, the sum, which I call an, would then give you an approximation to the total area enclosed between the curve and between x equals to a and x equals to b. The Riemann sum is the value of an in the limit where you make the norm of the partition goes to 0, and this could then be written as the limit of norm p with the sum of delta ai, where delta ai is just delta I times h. So here h is just f at ci minus g at ci multiplied with delta I, where I runs from 1 to n. Once you have obtained expression for this sum, then you take the limit of letting n goes to infinity, which is equivalent to norm going to 0, approximately speaking. Then you will be able to show that after some steps of algebra, this Riemann sum could be proven to be just simply given by f of x minus g of x integrated over x from a to b. That is how you arrive at the exact value of the area enclosed between the upper curve f and the lower curve g for x bounded between a and b. This area is just given by this very simple formula. So that is the way how to calculate the area enclosed between the two curves, and this slide just show you the details of the derivation for that formula. Let us try to look at example to calculate the area enclosed between two curves. The first curve is the function 2 minus x squared. Second curve is y equals to minus x. In this particular example, we have a curve of y equals to 2 minus x squared. And we have another so-called curve y equals to minus x. The y equals to minus x represents the curve sitting at the bottom of the area. So we call this gx, where gx is simply the minus x. Here, 2 minus x squared is referring to the function sitting at the top of the area to be integrated over, and here is the intersect between the two curves. If you solve the intersections, then you find that here the coordinate of the intersection between f and g is minus 1, whereas here it is 2. The coordinate for the intersection is minus 1, and here the intersection is 2 minus 2. Therefore, the area enclosed between the two curves shown as the region in the yellow color highlight could then be easily calculated to be the difference between the curve sitting at the above of the area, which is f, minus the functions, which is the curve sitting at the bottom of the area, which is its boundary given by g of x. Then you integrate over the difference between f and g from the lower limit of minus 1 to the upper limit of 2. Here we integrate over the variable of x from x equals to minus 1 to x equals 2. Then you just fill up this formula for f and g. F is 2 minus x squared. G is minus x. And you integrate with respect to x from minus 1 to 2. Then you obtain integrations of 2 plus x minus x squared from minus 1 to 2. This gives you 2x plus x squared over 2 minus x cubed over 3. Then you take the difference of this function between x equals to 2 and x equals to minus 1. Fill up all the details. You will arrive at a value of 9 over 2. That is the area between the two curves. The conclusions of this example is that you need to know what is the function sitting at the top of the area and the function sitting at the bottom of the area. Then you form the difference between the two functions and you integrate over x from the lower limit a to b, where a and b is the coordinate of x, where the area is bounded. The important thing to note is that when you do this, you are integrating with respect to x. The reason why you integrate with respect to x is because when you obtain this formula, you are actually partition the area along the x-axis. Let us now look at example 5 for calculating the area of another graph. In example 5, we have a function that is in the form of a square root of x, and it is bounded from below by another function of the form x minus 2. So you have to calculate the area under the curve, which is bounded by the square root of x and the functions of x minus 2. So here, in order to perform the calculations using the method that I mentioned earlier on, what you do is here you would call this a function of f. Then the upper functions is the function that is bounding the upper region of the area, whereas we call the function g of x to be the function bounding the lower boundary of the area. So in order to perform the calculation for the area is given as f minus g x. But you have to be very careful because if you look at these integrations, you have to put in the limit of a and b. So where is the limit? So if you were to do that, you cannot put it from say from 0 to this number, because if you do that, then what you are calculating is actually the integrations that is only for this particular area. So to perform the integrations for the area, you have to separate the functions or the calculations into the parts that is defining the area in this region, as well as the integration from here up to here that indicates the region defined by these sections. You have to divide the integrations from 0 to a and from a to b, where in the integration from 0 to a, the area that is to be integrated is only bounded by the function of f. So in that case, you would write down integrations of fx from 0 to a to indicate the area. I call this a1. Whereas for the area, which I will call a2, is bounded by this region, and I call this a2, where a2 is then given by the integrations of the difference between the upper boundary f minus the lower boundary, integrating from a to b. So in this example, you have to separate the calculations of the region into a1 and a2, and for that purpose, you have to know what is the values of a and b for the intersections of the functions at this point a and at this point b. So let us try to calculate what is the values for b based on these two functions. So to calculate the values of b, you have the situation where the functions of f at point b is the same as the values of the function of g at point b. And here b is the square root, where f of b is the square root of b, and the values of g at b is then b minus 2. So you can easily solve this problem. So what you do is that you square on both sides. Then you have b on the left. Then right hand side you have b squared plus 4 minus 4b. And you make some slight changes of the arrangement of b. Then you get b squared minus 5b plus 4 equals to 0. Then you solve these quadratic equations, and what you get is b is equals to 5 plus minus b squared minus 4ac. C is 4, this is 2. So this is just the usual solution for the quadratic equations in b. So you solve this further, it will be 5 plus minus b squared over 2. So here you get 4 or 1, right? So here you see that b is either equals to 1 or 4. So this is actually the values of b, which is equal to 4. It may appear that 1 is the solution to the quadratic equation. However, we will rule out b equals to 1 as a solution for the very simple fact that when you slot in b equals to 1 into this equation, it doesn't make sense. So if you set b equals to 1, then you have minus 1 equals to 1 minus 2, which is minus 1, which is obviously not correct. The reason why b appears to be equal to 1 in the solutions come from the fact that we are squaring this equation. So when you square the square root of b, then you get rid of one of the sign, and that will give rise to a spurious solution. A spurious solution meaning that a solution that is not valid. Anyway, when you equate and solve for the values of b, the b should be 4 and it should not be equals to 1. So once we have obtained that, then we know that this is equals to a 4. Then you can actually also work out the values of the function at this level. When b equals to 4, then this value, which designate the coordinate at the point of intersection between f and g, is 4, and the two come from the fact that you slot in 4 into the square root and then you get 2. This is obtained from the function of f. So up to this point, what I have told you is that here, in order to calculate the area, you have to form the sum of the two area, and you have to perform the area calculation for A1 and A2 separately. And in order to do that, you need to know what is the intervals of integration for A1 from 0 to A, and you need to know the interval of integration from A to B. So you need to know where is A, where is B. So this calculation is actually a bit cumbersome. Of course, you can proceed to perform this integration, and this is just the way how you obtain the solutions for this example 5, and then you arrive at the correct answer when you perform the calculation using this manner.